Hey everybody, you might be wondering, what did the game that you just played have to do with quantum? Well, let me show you. Let's think about the essential differences between what you played and the classical game of Connect 4. What you played, the token value was based on probability. It wasn't always one color or the other. It was sometimes a probability. And you had different ways of measuring the outcome. In fact, different times at which you were allowed to measure the outcome. And the mode or round you were playing determined that. That's also very similar to quantum, but we'll talk about why. And the final one is that based on those limitations of when measurement occurred, it changed the strategy that you used to try to win the game. So how you play is affected not only by the fact that there are probabilities, but also by when you're allowed to measure and find out what that result of the measurement is. All right, so let's think about that token again. So that means that that token value was based on probability, and it allowed two values to be stored in the token as long as it was it had a probability. So that's called superposition, and that's actually true in quantum. We can set it up so that a single object has one of two values, and then we measure it later and find out which one it measures at that moment. But it is storing them both when it's storing them. And we provided you a visual that was the probability of each value being measured, and you didn't have control over which outcome it would be. All you had was the information about the probability. The same is true in quantum. So in quantum, we have something called a qubit, hence the name of the game. And it holds one piece of information in a quantum system. And it can be either a 0 or a 1, and we'll depict that as black or white. But unlike classical systems, we can use this what's called an H gate, and we can cause it to not just have the same outcome based on the input. So we could put a black ball into this H gate, and sometimes I would get out a black ball, and sometimes I would get out a white ball. And to be more precise, what happens is I put the white ball or the black ball through, I apply an H gate to the black or the white, and then I perform a measurement. And there's a 50-50 probability of measuring black or white. So this is the way we introduce superposition into a quantum system. There are other gates that can do other percentages as well, but we're just showing the H gate because it's the classical one to present first in quantum. All right, so the other interesting thing about measurement is that once measured, now it no longer is in superposition. So if I measure it again, it's going to be black again. So if it has the result of black and I keep measuring it, it will always have the result of black. Okay? However, if I put it back into an H gate, that puts it back into superposition again. And now when I measure it, it's a 50-50 probability. So measurement not only gives you information about the state, but it fundamentally changes it so that it's no longer in that superposition. There are other ways that measurement can affect it. It doesn't always take away all of the superposition. Maybe it just changes the superposition. But for our purposes, we're saying it collapses it. Okay, so you were able to choose from 3 types of measurement: measurement when dropped, measurement at the end, in the order of when they were dropped, and measurement at the end in order chosen by players. Okay? And which one you chose changed your strategy. And that is the same as in quantum programming. So if you're trying to program a quantum computer, you have to be very careful about when measurements will happen because you don't want it to change the values in your system. You have to adjust your algorithms based on trying to minimize measurement and when those measurements will occur.